Okay, I'm going to spend a third lecture on problem solving, just working out even more problems. Okay, so again, just reminding you, our momentum equation, momentum is conserved, kinetic energy, we've got the total energy right here, which you can write either one of these two forms, and it's also conserved. And then we had the relationship between momentum and energy. And remember that if you're not moving, you have no momentum, E is just mc squared. And if mass is equal to 0, then the energy is just P times C, the mass of the object. Okay, so again, I just wanted to, again, working out more problems from that textbook. I'm going to go and do number 26. So this is number 26. Now here, they say an object having a mass of 900 kilograms. I'm not going to, from now on, I'm just going to say it's M1, but I know what it is. It's 900 kilograms. I'm just going to leave it as M1. It's given. And it's traveling at 0.85 C. U is equal to 0.85 C. 0.85 C. And it collides with another object out here, M2, and they gave it to me as 1,400 kilograms. These are big objects right here. But I'm just going to call it M2. I know what it is, and I should just call this U, and I know what that is too, so I don't have to plug in these numbers. Now it says these two objects stick together. The two objects stick together. And we can see again, when they stick together, they're going to be moving out this way at some velocity, some other velocity right there. And what do they want us to find? They just want us to find the mass of this composite particle. What is big M right there? But this one we know has to move because momentum has to be conserved. So I know this is moving. Okay, well, what do? I always look at the momentum equation. So here we've got, this one has momentum, that's at rest. So the only momentum we have is P M1, the momentum of him, plus 0 equals the momentum of this, which is equal to the momentum of afterwards. Since they're both the same, I don't even need a subscript on them. I'll just call them both P. They both have the same momentum. Now I'll look at the energy equation. Right here. The energy. Well, I do know how much, since they gave me U and they gave me M1, well, heck, I think I'll just find it from right here. I know M and I know U, so I got the total energy from right here. So we just got M1 C squared all over the square root of 1 minus U squared all over C squared plus the energy of that. Well, that one's not moving, so all of his energy is just MC squared plus M2 C squared. And that should be equal to the energy of this right here. Now I could either write this energy as, I could write it like this, but I don't know the speed of it, so maybe I shouldn't use this one. I could write the energy over here like this, but I don't know the kinetic. Maybe I'll use the energy from this. I'll take the square root of both sides, so E is the square root of this right here. So the energy of this is the square root of P. It doesn't matter, both P's are the same, P squared C squared plus big M squared C to the fourth. So I have this equation right here, but I have two unknowns. I don't know P, I know they're both equal right here, and I don't know M. That's what they wanted right here. Well, maybe I can get it from that. You notice just this one equation, just this one guy right here, his momentum, I can get it because I can just use this equation right there. It's just m1 u, and they gave me both of those, all over the square root of 1 minus u squared over c squared. Okay, so I have this and I have this. I think I can find now big M. So all I have to do is take this and I could just plug it right up into there. And these, I know that number, that number, that number. I know every one of these other numbers right here. I can solve for big M. Maybe I won't even solve for it. You know how to do it. It's just plugging in right here, and we plugging in. You could get this number, you could get that number, and you could get that number. So all you got is a bunch of numbers right there. Okay. What you're going to get is you're not going to get the sum of these two masses right here. It's going to be less than the sum of the two masses right here. Okay, well, let's look at another one right here. How about 31? Number 31. They say a particle of mass m moving with a velocity u, at least now they're using just variables, m moving with a velocity u, collides and sticks to a particle of m over 3 moving in the other direction. So this particle m over 3, and it's moving this way with also a velocity u, or speed u, right here. Then they stick together. So now they stick together. Now when they stick together, again, the mass is not going to be 4/3 m, right here. And what do they want? We want, what is the mass of this? Right here. Now, these two momentums aren't the same, so this thing is not going to be at rest afterwards. It's going to be moving, looks like in that direction right there. So it's still moving in that direction. Okay, well, again, we can write out the momentum equation. We got, going that way, we have the momentum, we call this momentum of m. We'll call it m sub m. So we got the momentum of this, and since this is going in the other way, it's minus the momentum of the m over 3 guy, and that should equal the momentum of this, p sub big M. So there's my momentum equation. Then we can plug in the energy equation. Well, we've got the energy of this one. Since they gave me the u, I'll probably use the same thing I did over here. And they gave me the m, so this would be mc squared all over the square root of 1 minus u squared over c squared. And then this one, you don't subtract the energy. These energies are scalar. You add it, plus m over 3. And it's going the same speed, c squared all over the square root of 1 minus u squared over c squared. So there's the energy of that one, and that equals the energy of this one right here. Now, they didn't give me the u, and they didn't ask for the u, so I'm probably not going to use this same equation. If they gave me u, I would, but I'll probably go back and use this one right here, since my other equation has momentum in it. So it'd be the square root of this momentum squared, p sub m squared c squared plus big M squared c to the 4th. Well, this, I know everything here, but I could add them together because this is, when I add these two together, it's just going to be 4/3 m. So this left side is just 4/3 mc squared all over the square root of 1 minus u squared over c squared. I know everything there. And that equals the square root of p sub m squared c squared plus big M squared c to the 4th. Again, there's two unknowns. I don't know either one of those two. But I could probably get it from right here, because I do know this momentum and I know that momentum. P sub m is the momentum of this. We'll just use the top equation over there, which is just mu over the square root of 1 minus u squared over c squared, minus m over 3u all over the square root of 1 minus u squared over c squared. Okay, and I can subtract these. That's 2/3 of 2/3 u all over the square root of 1 minus u squared over c squared. Okay, and I'll just take that and we'll put it right down into here. Okay, and so we end up with 4/3 mc squared, 4/3 mc squared all over the square root of 1 minus u squared over c squared equals the square root of this squared times c squared. Well, if I square this, that's 4/9 u squared, and then I'm multiplying it by c squared, divided by, there's an m up here too, an m from right there, m. So we get p, and then we have on the bottom, since we're squaring that, we get a 1 minus u squared over c squared, plus big M squared c to the 4th, plus big M squared c to the 4th. Okay, now I guess we'll have to square both sides to get rid of this square root. So this is 16/9 m squared, little m squared c to the 4th, all divided by this without the square root, 1 minus u squared over c squared. So that's all this squared, and it equals all this without the square root. That's equal to 4/9 m u squared c squared, m c squared, all over 1 minus u squared over c squared, plus big M squared c to the 4th. Okay, and then I think what I'll do is, I think I'll put another c squared here and another c squared down below, and that way there's a c to the 4th in every term. So that term and all of that and all of that cancels out. I can bring this term over to this side, and I have a common denominator. So I have big common denominator, 1 minus u squared over c squared. We have 16/9 m squared. And then bringing this thing over, we got minus 4/9 u squared over c squared. And that equals big M squared. Oh, this, well, I can pull out some stuff here. There must be an M over here too, an M right there. Okay, so it looks like, and then just take the square root of both sides. So it looks like big M is equal to the square root of this. So it's the square root of 16/9. Actually, I can pull out the 9th, so that's 1/3 out in front. We got 16 m, that should have been m squared right there. Why wasn't that m squared? Why, we squared both sides right here. That was m squared right there, squared. So we can pull out the m, so I'll pull that out. We got 1/3 m out front. We pulled out the 3, we pulled out the m's, So we're left with, and we're taking the square root of everything, 16 minus 4u squared over c squared divided by 1 minus u squared over c squared. I could even have pulled out another 4 out of that too. So m is equal to 2/3 m times the square root of, if I pulled a 4 out, this would be just left with a 4 minus u squared over c squared divided by 1 minus u squared over c squared. So there is the size of the particle right there. So and everything else was given right there. So it certainly isn't going to just be the sum of the two mass. It's not 4/3 m. If it was 4/3 m, this would have to be a factor of 2, and I don't think that factor is 2 right there. Okay, so here is just, again, you notice I'm doing pretty much the same thing on every one of these. I'm writing out a momentum equation and I'm writing out an energy equation. So this will help you on quite a few of the homework number 3s.